study what happens and make certain predictions. So we need to have a concrete model of what's going on in this dynamical system, and then we need to decide how to split the perturbations versus the unperturbed part, where the perturbation is usually assumed to be small, and so on. So the idea is that, okay, we want to go beyond this sort of splitting perturbed versus unperturbed with the idea that the perturbation is small. And of course, we want also results that are very general. We don't want to have like a concrete example of a discrete dynamical system where we have the evolution law and then we solve this thing directly, however hard it is. Instead, we want something very general. So we thought that, okay, that's the right avenue to use resource theories, because they allow us to have a framework that is independent of the concrete details of the system we are actually studying, but it can encompass like a large class of systems with similar properties. Okay, that's the idea, and therefore we use resource theories. And just we make a simplifying assumption, and the problem is already quite complicated in this case. So what we do, we work in the finite case. So we assume that we have a finite set where we have a dynamics, and this dynamic is generated by a generator of dynamics phi. But this generator is not assumed to be invertible in general. So the idea is that if we want to know how this dynamics works in after n times 10, we just take the nth power of this. But again, in general, we can only take n to be natural number, not an integer, because we cannot go backwards in time, roughly speaking. Then we also want to model situation where we have uncertainty on the states, and this will lead to another type of resource theory. And in this case, we introduce randomness. So without randomness, we have that the states are the elements of the system, and instead, if we have randomness, we introduce probability vectors, and we talk about the stochastic states. This is still very informal. Now I'm going to introduce things more formally using category theory. I just want to point out first that despite the introduction of randomness, the evolution still remains deterministic when we make this assumption. But however, the perturbation in this case, or the inference as we're going to call them, then will actually introduce some stochasticity in that, but we're going to see. Anyway, before we go into the categorical part, I want to introduce some basic terminology that will play a main role in this. So I just want first to explore what general features are present in a discrete dynamical system with a finite number of states. So since we have a finite number of states, we always have at least one cycle, possibly even of length 1, so just a fixed point, but can be of length greater than 1, which is a cycle in this case. So every point will eventually end up in a cycle, because essentially of the pigeonhole principle, since there is a finite number of states, the evolution cannot go on forever. At some point, it needs to repeat itself. So the idea is that an attractor, a cycle is reached after enough time steps. And there may also be transient states in this, which are states that are not part of attractors. Then, clearly, in such a situation, we can partition the dynamical system. Here it's represented as a graph, because we draw an arrow from two vertices if we can go from one vertex to the other in a single time step. So you see a blue basin of attraction and a red basin of attraction with their cycles. So now we say that the length of a state is the length of the cycle in its basin of attraction. So the states in the blue basin of attraction have length 4 because there is a cycle of length 4, and states in the red basin of attraction have length 2 because there is a cycle of length 2. Then we talk about the so-called transient progeny, which is the distance of state from its attractor in the same basin of attraction. So how many steps we need in order to reach an attractor? So in the red case, we need 2 steps. So we will have transient progeny D equal to 2. And instead, in the other case, that's for the 2 cycle, since they are already in a cycle, there is 0 steps that are needed to go to the cycle. Finally, we have a sort of dual notion, which is the notion of ancestry. And the ancestry is the distance of a state from its farthest predecessor. So how many steps we need to reach the state from its farthest predecessor. So if the state is transient, the ancestry is finite. And if the state is instead in an attractor, we say that it's infinite, because essentially its farthest predecessor is essentially itself by looping infinitely many times, and everything works well in that case. Anyway, let's go into more category theory slightly, let's say. So the idea is that, okay, we replace perturbation with inferences. And what are inferences? So if there is no randomness, inferences are simply function from the system to itself. And therefore, in this case, we are dealing with the process theory of sets and functions, something very standard. On the other hand, if we have randomness, we can consider the simplex of probability vectors on that system. And now we have stochastic maps from the system from the simplex to itself. And therefore, in such a setting, we have the process theory of stochastic maps. So what's the restriction we impose in such a setting? We definitely need to find a subcategory. And what we did was to impose the so-called covariance condition. So the idea is that inferences should commute with the generator of dynamics within their respective process theory. Sorry. Again, the idea is that somehow the inference respect the unperturbed evolution. The idea is that, again, if we impose this condition, we can actually prove that this covariant condition gives rise to a wide symmetric monodal subcategory of the category of inferences, whether the process theory of sets and function or the stochastic process theory. In any case, it will still give rise to a valid subcategory, and therefore a valid resource theory. Now, let's try to deal with the conversion problem. Now, in the deterministic case, the problem, despite being actually quite complicated to solve, it's still solvable in a very general setting, and that's the result we found. So suppose we have 2 deterministic states, S and S prime. The question is whether we can find a deterministic covariant influence that maps S into S prime. Okay, so what we did was this theorem, what we found. Okay, which gives necessary and sufficient conditions. So it's actually quite a complete result. So it just gives the one direction, also the other one. So it just solves the conversion problem in both directions. So I can actually go from S to S prime covariantly, if and only if, and there are a few interesting conditions. The length of the target state, which is the length of the corresponding attractor, divides the length of the original state. The transient progeny decreases, so the state becomes less transient. And the state of the target state S prime and its successors also are farther away from their predecessor than the state S and its successors. So we have this set of conditions that allow us to completely characterize the conversion problem. Okay, so notice that the 3 conditions are all involve order relations, because we have divide and then the standard less than or equal to or greater than or equal to. So in fact, what we found here is actually a complete family of monotones. One is the length. The length goes from the set of resources pre-ordered by the conversion and with the divisibility rule. That's actually an interesting case, because one of the examples where essentially you have a situation in which you have a partial order set. So a monotone that will produce a value that's in a partially ordered set and not in a totally ordered set. And the other one instead are in a totally ordered set, the transient progeny and the ancestry with the opposite direction. So we only need to check d prime minus 1 ancestries. D prime is the transient progeny of the target state, because the other inequalities are all satisfied. And therefore, we only have a finite number of inequalities to check. In particular, in the worst case, we have 2 plus the maximum over the progenies of all the states, let's say, in the dynamical system. So this is very convenient because we have a finite family. Now, let's briefly go through the stochastic case. The stochastic case is actually much more complicated. Now we represent the inference with stochastic matrices. We want to see whether, given 2 probability vectors P and P prime, we can go from P to P prime using a stochastic matrix. And this time we were not able to give like very concise conditions in general for the conventional problem, but we actually show that this actually can be phrased as a linear decision problem, which amounts to deciding whether a homogeneous system of linear equation has a solution or not. That's basically what we found in this respect. But now we can still say something quite general, because if we think of what the entries of a stochastic matrix are, they are just transition probabilities. The probability of going from S to S prime, this will be one of the entries of the stochastic matrix. Therefore, now we know that if the probability of going to S prime from S is 0, then clearly no transition is possible from S to S prime, even under a stochastic influence. So therefore, here we ask a new question. So we kind of work with the process theory of stochastic maps, but at the same time, we ask a question about deterministic states. So which entries of a stochastic matrix are 0, automatically 0? So which transitions are forbidden from deterministic states under stochastic covariant influence? And that's what we found, is that if rule number 2 and rule number 3 we found in the deterministic case, so if the transient progeny, the rule of transient progeny or the rule of ancestries are violated, one of them, then the probability of transition is 0. But funnily enough, now we can have transition that violate the divisibility rule. So suddenly we can overcome the divisibility rule if you allow randomness in the influences coming, let's say, roughly speaking, from the environment. So in other words, a randomness in such a setting is a resource because it activates transition between deterministic states that otherwise would not be possible in the purely deterministic case, because we have one of the monotones is actually the divisibility. So let me go to the conclusion. So we applied resource theories to discrete dynamical systems. And what we did, we constructed a monoidal subcategory of covariant inferences, both in the deterministic case, in which case was the category of sets and functions. The other one was a stochastic case in the case of stochasticity. In the deterministic case, we were able to find a complete family of monotones, which means a necessary and sufficient condition for the conversion. And in stochastic case, we were not able to do that, but we were still able to prove that the conversion problem can be phrased as a linear decision problem. And finally, the stochastic influences we observed that activate transition that otherwise would be forbidden if only deterministic influences are performed. And then I want just to say that, okay, here we have like an area that produced some interesting results. Now, the question is whether we can find other areas of science in general where we can try to apply resource theories guided by the principles of category theory in order to find interesting and notable results, and hopefully pave the way for new interdisciplinary connection between different areas. With this, I'd like to thank you for your attention, and I leave you with some references. Thank you very much.
Okay, thank you, Carlo. Thank you. So I'm going to ask if there are any questions on the audience. Yeah, much.
Hi, Carlo. Tomasz here. Thanks for the talk.
Yes. Yes.
And also thanks for taking this work on. It's very, very cool.
Yes.
I'm wondering what are some of the key examples you have in mind and in particular, maybe examples where the convertibility relation becomes like connected to an important problem that people care about. And maybe what I'm even more interested in is the stochastic case. If you have some.
Yeah, I guess you refer to this specific example we studied. Yeah, to this discrete dynamics. So the idea is that essentially something that is related to this problem, actually that was the thing that motivated us to go into this problem, was as I mentioned at the very beginning, the issue of genetic regulation. So basically, the idea is that you can we have the same DNA in every possible cell, but not all genes are expressed at the same time. Otherwise, we would have all cells of the same type. So some genes are expressed, some genes are not. Some people say, okay, we want to try to understand how this works. And therefore they basically model the state of each gene very, let's say, abruptly as very, let's say, in a very sort of rough way as 0 or 1, whether the gene is active or not active. In some cases, there are sort of intermediate cases as well, but it's either 0 or 1. So basically, you have then a dynamical system where your elements are your strings. Basically, you have a string where for every gene, you know whether the gene is active or not active. So it's a 0 or 1. And then you want to see how this sort of sequence of 0s and 1s evolves in time to understand how the activation of genes changes in time. And then make the simplifying assumption that the evolution proceeds in discrete time steps. So the situation is similar, and they build like sort of dynamical graph. And then what they do, people did in literature, they try to study using the tools of statistical mechanics and phase transitions and other things like that, which at the moment is not very easy to attack from the point of view of resource theories and all this framework of categorical framework, which I think it's actually a very interesting problem to tackle. And I encourage participants who are interested in this to start thinking about it, because I think it's really a very nice problem to try to apply these sort of techniques from category theory to the issue of phase transition and other things like that. But we kind of took a slightly different approach. We tried to understand what the role of the environment was in this setting. And therefore, the idea was, instead of trying to think what happens in the case of phase transition when I have an infinitely large number of genes or something like that, but there is no clear, let's say, action from the environment, that's to make the environment more explicit into the picture by introducing the action of the influence. And we are also in touch with some experimentalists who are interested in actually trying to test some of the prediction of this model into let's say on a concrete example of bacteria, let's say, to see whether some of the prediction we made are actually working. So as
Carlo,
to the
Carlo, I think we need to go to the next section.
Sure.
But thank you so much.
Anyway, no problem. Thank you so much for being here.
Yeah, thanks. I will keep some other questions.
Yeah, we can keep the discussion going for sure.
Also, there is the Sulip chat. They told me to tell you that you can continue the questions there. So we'll move the questions there, and we are going to start with the tutorial. Thank you, Carlo.
Perfect. Thank you so much.
Yes,
thanks.
Carlo.
Bye.